Okay, good morning everybody. Rainy day today. Good day to start our next topic, which is derivatives. So this is one of the two main topics of the course for which the course got its name, differential and integral calculus. So this is the differential part. So I want to start this with motivation. So motivation. And there are going to be two different motivations, one stemming from geometry and the other stemming from physics. And I'm going to start with physics one. So motivation one, is going to be from physics. And it's going to be instantaneous, is that correct? Speed. Okay, so suppose we have a particle or a car or whatever that's in motion, okay? And we're going to describe the position of the object by the function f, and it's going to be a function of time. So I'll denote the variable by t. So f of t is the position of the object at time t. Okay? So we have an object, it's moving, this is its position at time t. And what I want to know is, what is its speed? How fast is it moving at a given instant? Okay? You're driving the car, you're looking at the dashboard, and you can see that you're driving at 90 miles per hour. Too fast. 90 kilometers per hour. Okay? How do you know that? What does it mean that at that second you're driving at that speed? So what we do know is that if we divide the distance traveled by the time, what do we get here? Right. This is the average speed along a certain time period. Okay, so let's say we're looking at the time between time t and time t0. So t0 is the instant at which we want to calculate. So this is the time difference between time t and time t0. And the distance traveled over that time period is the position at t minus the position at t0. Do you agree? Okay. So the distance divided by time, this is the average speed. The average speed over this time period between t and t0, or t0 and t. Does everybody agree? So if we drove, let's say, from Haifa to Tel Aviv, 90 kilometers, and it took us an hour, that means that our average speed was 90 kilometers per hour. Do you agree? That doesn't mean we didn't get a speed ticket along the way, because maybe passing Hadera, we were driving at 150. Okay? So this is only average speed. How can we make this more accurate? How do we get a more accurate idea of how fast we're driving? Right. If the time difference here is very short, suppose we're not looking at an hour time difference, but at a second of time difference, and suppose we have an accurate way of measuring exactly our position at a second and at the next second, then this is the average speed over a second. That's rather accurate, right? Can we make it more accurate?
Half a second.
Right, take 1/10 of a second, right? Can we make it more accurate? Right. So the idea is that we want to define, so that's what I'm going to write, the instantaneous, I don't want to write this word again today. This is too many letters. The instantaneous speed at t0 is defined as, and we're we're grown-ups. We know the notion of limits. We're wise people. Is defined as the limit as t goes to t0, as t approaches t0, as this difference between t and t0 becomes smaller, of the average speeds. F of t minus f of t0 divided by t minus t0. Do you agree that this is a reasonable definition, a good definition? Okay. Okay. And in general, this motivation, f doesn't have to be position at time t. F can be temperature at time t, and we want to know the instantaneous rate of change of the temperature. Okay? So we can measure any rate of change of any function by this expression. Okay? So this is motivation number one. And this leads us to the following definition. Maybe I'll use a new board for it. Definition. And for the definition, I'm going to resort back to x as the variable, because usually x has nothing to do with time. We say that f is differentiable, that's the notion we're defining, at the point x0. x0 is now just a point. This is the abstract notion. If the limit, which we wrote before, limit x goes to x0, f of x minus f of x0 divided by x minus x0, if the limit exists. If this limit exists. If it exists, and by the way, exists, we mean exists and is finite. Okay? Usually when I say that a limit exists, I'm going to mean that it's finite. And if it's infinite, I'm going to say that explicitly. Okay. So if this limit exists, we say that the function is differentiable at the point x0. We denote this by, so there are two notations. One is f prime at x0. So f prime at x0 is defined to be this. Okay? Or, this is what's called Leibniz notation. I don't know if you encountered it. df divided by dx. And usually we say df to dx at x0. So these are two notations for exactly the same thing, this limit. Okay? And we denote this by that and call it, what do we call it? Right, the derivative of f at x0. Note that once again, just like continuity was defined by the notion of the limit, this is another very important notion in mathematics defined by limits. And note that once again, it's a pointwise definition. It's the derivative at the point x0. Okay? Okay. There is an equivalent definition. So equivalent definition. And I'm not going to write all the words again. I'm just going to write the limit, but in a slightly different way. And I'm going to show you in a minute why it's actually the same thing. So you can replace that limit we wrote there by the following limit. Limit, for some reason it's customary to take h here. H goes to 0. F at x0 plus h minus f at x0 divided by h. So what does it mean that this is an equivalent definition? It means that this limit and the limit we wrote before, f of x minus f at x0, are precisely the same limit. They give the same value. They exist if and only if the other one exists. Okay? And how do we see that? So to see that, take h to be x minus x0. So if h is x minus x0, then, well, we're going to have to bounce back and forth now. So look at this limit a second. This was our original definition. If h is x minus x0, then the denominator is just h, right? When x approaches x0, x minus x0 approaches what? 0. So that's why we wrote there h approaches 0. X, if x minus x0 is h, then x is h plus x0. That's what we wrote there. And this we didn't touch. So do you see that by this kind of rewriting of the name of the variable, we get precisely this? Do you agree? Okay. Okay. So this is the notion of the derivative and what it means for a function to be differentiable, and the motivation coming from physics. And now I want to show you the other motivation. So let's write the other motivation. So motivation 2 is going to come from geometry. Am I correct that all of you have seen this before? That this is not really new stuff to anybody? Okay, good. I'm still going to do it in full detail, but it's good to know. Okay, so the second motivation comes from geometry. And it's the slope of the tangent line. So here we're going to have a picture. So suppose we have a function. So here's our coordinate system, and suppose we have a function f. And I'm going to formally define everything in a second. This is just a geometric idea. So suppose I'm looking at some point, let's say this point, and I'm going to call it x0, and the value at this point is what? It's something like this. And I want to know what is the slope of the tangent line precisely at this point. Okay. Now, the reason that this is still an intuitive discussion is that we didn't define what the tangent line is. And in fact, the formal definition of the tangent line is going to be by the derivative. But suppose we understand what we mean. We want a line that passes through this point and touches the function at this point only, at least in a neighborhood or something like that, right? We know what we want in some sense. What is its slope? Okay? So the way to do it is to say, okay, what we do know is, suppose we take another point here, any point, then we can easily define what's called the secant line, the the line connecting these 2 points. Okay, so let's say that this point, let's try to build up to the equivalent definition. So I'm going to call this not x, but I'm going to call it x0 plus h. Okay? And I can easily say what is the slope of the line connecting these 2 points. Okay? Why? What is the slope of a line connecting 2 points? It's the difference in the y values divided by the difference in the x values. Do you agree? So the slope of the secant, this line, is f at x0 plus h, that's the y value of this point, minus f at x0, that's the y value at this point. I didn't mean them to seem the same. That's just a coincidence. Okay? Divided by the difference in the x values. So x0 plus h minus x0, which is h. Do you agree that this is the slope of the secant line? But clearly, this is not the slope of the tangent line. But we can get a better estimate of the slope of the tangent line if we take our x0 plus h, the other point, closer to x0. Suppose it's here. Now this is the secant line, right? And this is, well, closer. But we can take it even closer. We can take it, let's say, here. And this is the secant line. This already looks pretty good. Right? You can take it even closer. I don't know if you can see what's going on anymore. I can, but that's because I'm very close. But is the idea clear? So the slope of the tangent line, which maybe I'll draw here in red, so this is the tangent line, this line here. The slope of the tangent line is the limit of the slopes of the secants as the other point, which determines the secant, gets closer and closer to x0. Do you agree? So we define, okay, so that's that definition. I already wrote it. This. Right? Everybody? Okay. So, in order to formalize this, I want to define the tangent line. So definition. If that limit exists, and it's not always going to exist, we're going to see many examples today. If that limit exists, if f prime at x0 exists, another word of saying it is if f is differentiable at x0, then the straight line y equals f prime at x0 times x minus x0 plus f at x0, we'll decipher this in just a second, is called the tangent line of f at x0. So this is the definition of the tangent line. And why is this the definition? Well, I want the tangent line to be, let's take a step back to this picture. I want the tangent line to be precisely the line passing through this point. This is the point x0, f of x0. That's this point. Do you agree? Whose slope is precisely f prime at x0. Okay? So how do I get a line when I know a point it goes through and a given slope? So So the explanation to this, so I want a line of the form y equals ax plus b. I want the slope to be f prime of x0, so I want it to be y equals f prime of x0 times x plus b. And I want it to pass through the point x0, f of x0. So if I plug in f of x0 here and x0 here, that should give me the b, right? So f of x0 equals f prime of x0 times x0 plus b, and therefore b is this minus this. So b equals, so a is f prime at x0, that's the first thing I demanded, and then the second is that b is f prime at x0 times x0 minus f at x0. And now I plug this back into here, and I get precisely this. Should be the opposite? Wait, why? Ah, right, right. It's this minus this, sorry. Let me do it minus and plus like this. Then I don't have to erase everything. Okay, there's a minus here. Do you agree that this is precisely the only line with slope f prime at x0 passing through the point x0, f of x0? Okay, so that's how we define the tangent line. And its slope is precisely the limit of the slopes of the secant lines. Okay? Now, we will see, so this was just some calculations, if you haven't seen it before, to see where this comes from. We will see later on, in a week or two, a very important feature of this tangent line in our discussion of approximations, okay, and Taylor polynomials and so on. And for now, we're going to put the tangent line aside. I just want to make a remark. You may have seen in your previous studies, like in high school or wherever, and it's common to see some false intuitions, okay? Some false ideas of what the tangent line is. For example, many people think that the tangent line is a line going through the point which does not cross the graph of the function. That's not true, okay? So, remark, some false intuitions So for example, it's not true that, suppose we have a function, that the tangent line does not cross the graph of the function. Take this point, for example. Take the tangent line. There it is. It crosses the graph of the function. Do you agree? So it's not true to say that the tangent line does not cross the graph of the function. Do you agree? Some people say, wait, but it crossed the graph of the function far away from this point. Maybe close to the point it doesn't cross the graph of the function. That's still not true. Look, for example, at the function, a function you know, a function x cubed. So that function looks like this. So this is x cubed. Here I just doodled something. And what is the tangent line? Let me use that red again. What is the tangent line at 0? It's the x-axis. This is the tangent. Well, it's hard to see here because everything is, let me make it in kind of bold red. Okay? The tangent line at 0 is the x-axis. It crosses the function at any neighborhood. Can you see this, or is this too small? But you can draw it bigger in your notebook. Okay? So it's very not true to say that the tangent line is a line through the point that is only on one side of the function, or does not cross the function, or all kinds of intuitions like that. It's not true to say that it intersects the function only at one point. Well, here's an example. It intersects at 2 points. So all these intuitions are false. Okay? And the only real definition is it's a line whose slope is the derivative and goes through that point. Okay? That's the tangent line. Okay. So now that we have the definition, I want to start calculating some derivatives in order to clear up enough board for us. Maybe I'll write both definitions here and leave them throughout today. So f prime at x0 is defined as the limit x approaches x0 of f of x minus f of x0 divided by x minus x0, or this limit. And these are the two equivalent definitions. And of course, the limit does not necessarily exist. We'll see examples. If it exists, we say that the function is differentiable at x0. Okay. Now I can erase this. And let's start calculating some derivatives. Okay, so examples. Example 1, let's take the constant function. F of x equals c. C is some constant. So what does it look like? I'm going to draw the constant function for you, a constant function for you. Ta-da! What's the slope at a given point? 0. Do you agree that whatever we do, the answer better be that the slope at any point is 0? Okay. But let's do it formally using one of those two definitions. So for any x0, it doesn't depend here what your x0 is. F prime at x0 is what? Is the limit. Let's use the first definition. X approaches x0. F of x, what is f of x? C. Minus f of x0, c, divided by x minus x0. Do you agree? Now, the top here is identically 0. The bottom is not. Do you agree? So this expression, for any fixed x, this expression is 0. Therefore, this is a limit of zeros, and that limit is 0. So the derivative of a constant function is 0 at any point. And note here something that's always going to be the case. Always. Derivatives, this expression, is always an expression of the form something that goes to 0 divided by something that goes to 0. It's always of the form 0 over 0, which is undefined, and which was one of those things we had to work for when we discussed limits. Okay? So arithmetics never holds. Okay? Good? Okay. So that's example number 1. Example number 2. Let's take the second easiest thing one can think of. F of x equals x. What's the slope of this function? Again, at every point. What's the slope? 1. So let's see how that happens. So f prime of x, of x0, at any x0, again, this calculation is going to hold for any x0, is what? Is the limit x approaches x0 of f of x. What is f of x? X. Minus f of x0. What is f of x0? X0. Divided by x minus x0. So this expression is always 1. The limit of the constant function 1 is 1. Fixing a 1 with a long nose is not hard, not easy. Good? Questions? Okay, let's do another example. Example 3. Let's do f of x equals root x. So let's draw it. Root x. All these drawings that I'm making are just to remind you what these functions look like, but I really, really hope that at this point in time you all have them, well in your head. When I say root x, before I finish saying the x of the root x, you already see this picture in your head. Okay? And you should be at that point. That's an extremely useful tool to have, these pictures in your head when we talk about formulas for functions. Okay? ln of x shouldn't be just saying something. It should be this. E to the x, it's this. Sine x. You should feel these functions. You should be buddies. Okay, root x. So I want the derivative, f prime. What is f prime? At some point x0. So again, I'm going to resort to the definition. Let's use this one this time, because we used this a couple times already. They're equivalent. Doesn't matter what you use. Usually they're as easy or as hard to calculate. So it's the limit. H goes to 0. F at x0 plus h. What is f? Root. So it's root of x0 plus h minus the root of x0 divided by h. Do you agree that this is the limit that I want to calculate? Okay. Do you know the standard trick to use here? Right. Multiply the top and the bottom by the conjugate of the difference. Okay. So I'm going to multiply top and bottom equals multiply top and bottom by the conjugate. By the conjugate we mean take the same expression but with a plus. x0 plus h plus root x0. And the reason to do that, well, if you've used this trick, oops. Yeah. Sorry about that. So the reason to do this is then we can use the formula, the algebraic formula, a minus b times a plus b is a squared minus b squared. Right? So here's what we get. So we get the limit as h goes to 0. The bottom is going to now have this expression in it, but with a plus, which is good. Right? The reason that we couldn't do this right away is because, again, it was a 0 over 0 situation, in quote marks. Right? When h goes to 0, this goes to root of x0, so this difference becomes 0. But when we do the sum, that's no longer an issue. Right? And the top is this times this. Right? So it's a minus b times a plus b is a squared minus b squared. A squared is x0 plus h. B squared is x0. Is everybody following? So their difference is just h. Did everybody follow this step? Or do I need to say it? Can you multiply these two? What's the product? This squared minus this squared, right? That's an algebraic formula. This squared is just what's written inside the root. This squared is x0. Their difference is just h. And now I can cancel out these two h's. So I just get this. And what's the limit as h goes to 0? The limit is 1 over 2 times the root of x0. So that's the derivative of root x. The derivative of root x is 1 over 2 root x. Okay? And this is true for any x 0 greater than 0. This function is not defined. It's not defined for negative numbers. Right? No, greater than. At 0 itself, I cannot take this limit because when h is negative, again, I'm going to get here. If this is 0, I'm going to be in the restricted zone where this function is not defined. Okay, so I can't do this for x0 equals 0. This function is not differentiable at 0. There is going to be a notion in a few minutes of being differentiable from the right and being differentiable from the left, just like we had for continuity. And then we are going to be able to say that this function is differentiable from the, well, in fact, not. We're going to be able to do this calculation, but when we get here, the limit is not going to exist. Right? We can't divide by 0. Okay, we'll get there. Clear? Questions? Okay, so that's example 3. Let's do another example. Let's do another example. So, calculating derivatives boils down to calculating limits. If you know how to calculate limits, you know how to calculate derivatives. But if you don't know how to calculate limits, then you better go learn, right? Okay. Example 4, f of x equals sine of x. Let's make a quick drawing. So sine of x looks something like this. Do you know what the answer is going to be? Right. The answer is that the derivative at any point is cosine. Right? Let's see how that, how we get that from the definition. So f prime at x0 equals the limit. Let's use the h version again. H goes to 0 of f, which is sine, at x0 plus h, minus f at x0 divided by x minus x0. This is the, divided by h, sorry. Divided by h. This is the limit we want to calculate. Right? What do we do here? What can we resort to here?
Trigonometry.
Right, trigonometry. So there's a formula for the difference between sine A minus sine B. Okay? And you may not remember it by heart, but I'm going to remind you what the formula is. So, in general, sine alpha minus sine beta equals 2 sine alpha minus beta divided by 2 times cosine alpha plus beta divided by 2. So this is a known trig formula. Personally, I don't think you should remember all these formulas by heart, but you should know they exist. So when you get here and you don't know what to do, one of the things that should pop into your mind is, wait, I know there's a formula for this, and then look it up. That's my take on this issue. Some people expect you to remember all these by heart. I don't. Okay, so how do we use this? So lim, h goes to 0, and what do we get here? Sine alpha minus sine beta, so we get 2 times sine of the difference divided by 2. The difference is just h divided by 2. Do you agree? And then multiply that by cosine of the sum divided by 2. So the sum is what? Is 2x0 plus h divided by 2. That's the sum of the arguments of the sines. And all of this divided by h. Do you agree that this is what we get? Say yes.
Yes.
Thank you. Okay. Now what can we do? Right. I'm going to look here a second. I'm going to do something that you shouldn't do in your notebooks or when you're writing anything, but I'm going to do it now. I'm going to take this 2 and divide h by 2. So instead of multiplying by 2, I'm going to divide by 1/2. So this 2 is going to appear here. Does everybody agree to that? I was lazy. I didn't want to write all this again. And now, when h goes to 0, this factor goes to what? 1. So it's sine of something divided by that same something, and the something is something that goes to 0. So this goes to 1 as h goes to 0, right? What about this factor? What does this goes to? So as h goes to 0, we get 2x0 over 2, which is x0. So the limit is just cosine of x0. So the derivative of sine is cosine. Good? Everybody? What does it mean that the derivative of sine is cosine? What does it mean? Well, geometrically, for example, what it means geometrically is that if you look at a point, suppose you look at the point, let's make a bigger drawing so we can see it more clearly. Here's sine zoomed in on so we can better see what happens. So here's sine. And suppose we look at the point here, pi over 2. What's the derivative of sine at the point pi over 2? It's 0. 0 is precisely cosine of pi over 2. Do you agree? So the slope of the tangent line, here's the tangent line, the slope of the tangent line at pi over 2 is cosine of pi over 2. What's the slope of the tangent line? Let's say what's the slope of the tangent line? Let's say at pi. So this is pi, and here's the tangent line, not 1. Here's the tangent line at pi. What's the slope? -1, which is precisely cosine of pi. Do you agree? So that's what it means when we say that the derivative of sine is cosine. The slope of the tangent line at any point to the function sine is precisely cosine at that point. Good? Okay. Good. So there's another example that I thought of doing, which is useful, but maybe you'll try this one on your own. So I'm only going to leave one line for it because I'm going to let you guys try it. It's not trivial. Okay, you have to work on it a bit. So try to find the derivative of the function f of x equals ln of x. Picture, which you should, of course, all know, is something like this. That's the graph of the natural logarithm. So try to find the derivative. Okay? And let's just think the first few steps out loud. We're going to have this difference, but instead of sine, it's going to be ln, right? What's ln of something minus ln of something? Right, it's ln of the quotient. Do you remember that? So that's going to be your first step. And the ln of the quotient is going to be multiplied by 1 over h. When you have ln of something with a coefficient, that coefficient can go inside the ln as an exponent. Do you know that? Right? A ln of b is ln of b to the a. Right? So that's the kind of steps you're going to need here to exploit the features of ln, the properties of ln, in order to calculate this. And it's going to be related to limits which involve e, the limit of 1 over x to the power x, which we have seen and practiced. And what you should get is that f prime at x0 equals, do you know the answer? Right, 1 over x0. And this is for any x0 greater than 0, which is the domain of the natural logarithm. Okay, so try this. This is a very good exercise. Try it. Okay, promise? Promise?
On sine is for all x, right?
Yeah, for sine, this calculation was true for any x0. Okay, so now we've calculated quite a few derivatives, 4 plus 1 that you're going to complete on your own. And do you agree that it doesn't seem too tempting to calculate derivatives using the definition for the rest of our lives? Right? It seems like too much work. Right? So we don't want every time somebody gives us a function to resort to the definition and start calculating limits, although we're very good at calculating limits, right? We can do them like that, but still there must be an easier way, and you know the easier ways. So there are all kinds of formulas for the derivative of a sum and the derivative of a quotient, and that's what we're heading to. Maybe, yeah, so let me give you just one more example, then we'll take a break, and then we'll discuss those formulas. And so I want to give you an example where there is no derivative. Does anybody know the standard example? Right, that's a standard example. So let's look at f of x equals the absolute value of x. And this example and others leads to the intuition, just intuition, that a function, saying that a function is differentiable is saying that it doesn't have these pointy points, which are called cusps. Okay? So at a cusp, the function is not going to be differentiable, and that's the idea. So let's prove that f is not differentiable at this specific point, at x equals 0. So why not? In order to say that it's not differentiable, we have to show that that limit that defines the derivative doesn't exist, right? And why is it not going to exist? Because when we come from the right, what's that limit going to be? 1, right? Because it's the slopes on the right. When we come from the left, what's the limit going to be? -1. So let's show that. So the limit as, which one? Let's say as x goes to x0 of f of x, let's write right away, of absolute value of x minus, no, it's not x goes to x0, it's x goes to 0. Our x0 is now 0. We're claiming that there's no limit at 0. Of absolute value of x minus absolute value of 0 divided by x minus 0. That's the limit we want to calculate, right? That's the definition of the derivative for the function absolute value of x and for the point x0 being 0. Do you agree that this is the limit we want to calculate? Okay. So this equals the limit as x approaches 0 of absolute value of x divided by x. And, well, absolute value of x is x itself when x is positive, and it's minus x when x is negative. So we're going to have to separate this to the two one-sided limits. So when x approaches x0 from the right, we get, when x approaches 0 from the right, the absolute value of x is just x, right? So it's the limit x goes to 0 plus of x over x. This is just 1, so this limit is 1. Do you agree? When we do the same thing but approach 0 from the left, taking this one-sided limit, not of the function, of the definition of the derivative. So when we take that same limit but approach from the left, what's the absolute value of x when x is negative? It's minus x. So it's the limit x goes to 0 minus of minus x over x, which is negative 1. So the two one-sided limits defining the derivative both exist, but they're not equal. So the limit doesn't exist. So f prime at 0 does not exist. You just proved it by definition, and this builds to the intuition, let me write it here, which we said just a minute ago, intuition f is not differentiable at cusps. Or another way of saying this, and if you recall our very, very first lecture, remember we discussed the Fermat theorem and the Rolle's theorem and Lagrange theorem. Our intuition was that saying a function is differentiable is saying that it's smooth, has no cusps. Okay? That's where this intuition stems from. Okay? Good? By the way, those theorems are going to formally show up next lecture. We're going to actually see them and prove them and discuss them. Okay, any questions so far? Yes?
How is this the definition of the derivative?
This?
Yeah.
Well, let me show you on this board. Here's the definition of the derivative. F of x, absolute value of x, minus f of x0. x0 is 0. We're showing that it's not differentiable at 0. So absolute value of x minus absolute value of 0 divided by x minus 0 as x approaches 0. That's precisely what we wrote here. Okay? Because we're showing that it's not differentiable, not at any point, only at the point 0. At any other point it is differentiable. At any other point, well, here it's just the function x, and the derivative is 1. Right? And likewise for the negative numbers. Okay, so let's take a 10-minute break now.